Okay, so we'll continue what we were talking about yesterday, which is background cosmology. We said that large scales, much larger than the scale of a galaxy, the universe can be considered isotropic and homogeneous. For example, the density of galaxies will not differ from direction to another, or from one point to another. We measure it here, or here, or here. And we said we can use that fact to do a Newtonian derivation of the equation of motion of the background expansion, of the cosmic expansion of the universe. This homogeneous isotropic patch. This is from a picture, actually, of radio astronomy, of the whole sky, but we can imagine, and this is like taking this patch and making it bigger. So that's something what we're doing in the Newtonian approximation. We're taking a small patch such that the communication time between the galaxies, the way they talk to each other through the light speed, is not too large. We said we can use Gauss theorem for gravity. There's a Gauss theorem for gravity because the Coulomb's law is similar to Newton's law. So you can do like a Gauss theorem for gravity, like a Gauss theorem for electrostatics. And we got the force on a sphere. This is on the Earth as an example, but our patch, cosmic patch, is the same principle. It's universal gravity, so it should apply everywhere, at least when the Newtonian approximation is valid. This would be valid. Doesn't matter if it's the Earth or millions of parsecs, light years, or billions, or so on. It's all the same. And we said by something called the Newton-Birkhoff theorem that the patch outside the patch, it doesn't matter because they cancel out, and therefore our equation is quite simple. M inside the patch is constant, and this is simply the Newton's equation of motion for the patch of cosmic patch that contains many galaxies, but is small compared to something. What is the something? We have to solve the equation first. We said the equation is quite simple. It's like the Newtonian equation of ball thrown up on the Earth. Why? Because a ball thrown out to the Earth, the mass of the Earth is constant, and we just integrate it. When we integrate it, we get an energy integral. This is called an energy integral. It's a constant of motion of the equation. Energy is a constant of motion. The constant of integration is called energy in mechanics. Okay? And the ball can go up, but if you throw it really hard, the ball will escape. It will reach the escape velocity. And in cosmological terms, we will see that this is the difference between a universe that expands and recontracts and one that always expands. Okay? And we said that we can take the scale of the ball out, and we can rescale it, and also use the densities m over volume Rs cubed, A cubed, the volume, and get this sort of equation with another constant now that we don't know what it is. It seems quite interesting because it's the same for all expanding spheres. But in the Newtonian limit, it's not clear at all what it could be, so we need to go further. Another thing in the Newtonian limit that is not clear at all, with this equation, we already have a Friedmann equation, this is called a Friedmann equation. But it misses what the constant is, and it misses what if the universe is not only made of galaxies, but is made of things that are relativistic. Not gravity relativistic, but the content is relativistic. Photons, for example, are necessarily relativistic. Neutrinos will be, at least for most of their life during the universe, depending on their mass. Anyway, but we said that our Newtonian limit would be valid within a patch smaller than the Hubble sphere. What is the Hubble sphere? It's a sphere of a radius of a Hubble time. What is the Hubble time? It's extrapolating a tangent to the solution such that the universe doubles its size. So the Hubble time is like doing a line. If this is our time here, if this is our evolution of the universe here, this is like drawing a line here would be the Hubble time. So it's quite close to the real age, so to speak, of the universe since the beginning of the expansion. So that's why, for these models at least, not for the inflation models, because these would be, the curve here would be, during inflation, would be exponential, so a tangent will not reflect very much the age. You know? But for models like that, where there's only galaxies, that's what we considered up to now, only galaxies. No inflaton, no photons, no neutrinos, no things like that at all. Okay? But what do we do if we want neutrinos and photons to start with? Inflatons later and cosmological constant and dark energy. Let's start with things we know to exist. We need to take them into account. Due to Gauss' law, this is the field theory equivalent of the Newtonian gravity, Poisson equation. You probably know Poisson equation from electrostatics, right? Poisson equation, electrostatics, where you have epsilon naught here, 1 over epsilon naught, the permittivity of free space. No, this is G here instead of epsilon because this is gravity. So the constant is going to be G. Okay? So this is Poisson equation for gravity, basically Newton's law in field force. Newton's law for F and m over r squared minus. This is Newton's law. Okay? So for gravity. Well, Poisson equation for gravity is Newton's law in field theory form. Right? Okay, so we need a relativistic analog with this. Even if we start with special relativity, you know that things like momentum will have to contribute. Because this is like in special relativity how it is. Can we put momentum here? We probably can't. Because here is a density, and a density actually, even in, like if we want special relativity, it will not transform like a scalar or a vector. It actually looks like it transforms because it's m over r. In one direction r, it's r cubed, but let's say we go in one direction. And m has a Lorentz factor, and r has another Lorentz factor inverse. And 1 over gamma times gamma is gamma squared. So this looks like it transforms like a component of a tensor, two transformations. Not 0 like a scalar or 1 like a vector. So you can't put it here. It doesn't transform like a scalar. So what do? We need a tensor, including the momentum. Well, this thing is already there. 9 of its components, it has to be 16 in GR because it's space-time, but 9 of its components are already there in fluid mechanics. It's called the stress tensor in fluid mechanics and kinetics here, depending how you like to look at these things. So if you want, I can move through this quickly. So these are fluxes, momentum and energy fluxes. Flux is the amount of things that pass through unit area in unit time. That's a flux. Okay? So if we have a cylinder of unit length, a guy like that, okay, the amount of flux, L equals 1 and A equals 1 here, some unit. The amount of flux of mass through this cylinder is rho v. Is that clear? The amount of mass that goes through unit area from a cylinder of unit length is rho times the velocity. Mass density times the velocity, so that's how much mass is going through here. And this is also the momentum density, rho v. Yeah. mv is the momentum. Rho v, momentum density. So rho v squared is the momentum flux. So this is momentum density, mass flux. My handwriting is as bad as not doing it. So this is momentum flux. momentum density, mass flux. And this is momentum flux. Now, if I have different VI and Vj, then the momentum flux would be VI, Vj in different projections of VI on Vj. I have ماسورة ومش الفلكس بتاع المومنتم مش عمود عليها انما في شوية طالعين فهيبقى في تنسور كومبوننت VI, Vj. سرعة البتاع مع الدوت برودكت بتاع الاريا بتاعت البتاع اللي هي عامله زي كده. Equals 1 بس that's a vector. So مش هنا. So this would be VI, Vj and هي equals 1. Okay, so and there's a technical point. Strictly, this is for an ideal fluid, strictly speaking. If it's not an ideal fluid, I need to take the particles, not fluid particles. A fluid particle, fluid mechanics is a box containing many particles but small compared to the size of the system. It's another idea similar to our galaxy, small compared to the horizon but big box containing many galaxies. A similar idea is in fluid mechanics, a box containing many molecules, for example, or galaxies in our case, or whatever, and small compared to the size of the system. That's a fluid element. But if you want to do things properly and want to include viscosity, then you should take over molecules and do an average, and this produces viscosity. Okay, so there's a technical point, but not important for us here. Maybe I'll talk about it a bit more tomorrow afternoon with the turbulence stuff, time permitting, but not important here. Because in cosmology, everything is nice and ideal fluid, at least from standard cosmology, so we don't need these complications here. But anyway, so here we go. Energy density, this guy. Energy flux, this guy. And momentum density, this is symmetric. 16 components, only 10 are independent. So the energy density is the same as the momentum flux. Right? And then these are the cross terms, VI, Vj. ماسورة والمية طالعة مش عمودي عليها. VI, Vj. And these are the isotropic terms. VI, Vi squared. V1, V1 squared, V2, V2 squared, V3, V3 squared, and so on. And that's it. This is our energy momentum tensor. These exist already from hydrodynamics in the lab. And these are relativistic things. Well, the ones in yellow and red. Well, yeah, the ones in yellow and red are relativistic. Okay? So, and it's a symmetric tensor. So this is our energy momentum tensor. This is the hydrostress tensor, IJ23. Anything else on that? I don't think anymore. So this is our tensor. Now, this is quite complicated, obviously, as Adil was saying, 10 equations and so on, and we're going to have to do there's a slide missing in here. Oh, okay, here we go. But it becomes very simple in cosmology. Why? Because things are homogeneous and isotropic. Okay? So therefore, if you're homogeneous and isotropic, there will be no streaming terms. مفيش ترع. مفيش مية ماشية بترع. Okay? There is no streaming. Okay? And there is no cross terms, obviously. مواسير حاجات مش عمودي عليها. Otherwise, you don't have isotropic, obviously, if you have cross terms. And you don't have homogeneity, there are streams. Or maybe isotropy, I don't know, but yeah, but at least not homogeneity. So you don't have these terms. So what are you left with? The energy density of the Newtonian thing and the trace of the thing. The isotropic component of the stress tensor in classical hydrodynamics is called pressure. V1 squared, V11 squared, V22 squared, these are called pressures in hydrodynamics, okay? We call them pressures. They are rho V squared, basically. These terms we are left with. These will exist. They can exist because they're isotropic. These are the things. So you could have that in principle. There's no reason why not. Okay? So we can keep the pressure and we keep the thing. Heuristically speaking, it will be trace of the energy momentum tensor and we keep our Poisson equation. You can show that. And I can show you how to do it in detail. But I think it's fairly intuitive enough, and I'll show you another way of getting the same result. But you can do it from in the weak field and quasi-static approximation, which is what we need if we want to derive a Poisson equation originally from relativity. You can show that this is possible. Weak field because we're always in speeds that are, so to speak, smaller than gm over c squared by definition, because we're doing the Newtonian approximation. Okay, by definition, it would be that. Okay, you can show it, and there's a step-by-step way in how to show it in the exercise. But anyway, let's say we believe that because it's quite intuitive that we replace this guy by the trace. Okay, then we get this equation, which is the original 2-by equation, the break thing, but with another term, the 3 pressures over c squared, which you can imagine it has to be even by dimensional analysis. This is another thing you should learn. You cannot put p here and rho there, because p is rho v squared. We did. We know what p is. It's in units, at least in hydrodynamics, rho v squared. So we have to do c squared there to get our units correct. So this is our acceleration equation. Note that p, if it's very negative, this would be positive and the universe would be accelerating. Note. Right? This will change sign. Rho cannot, at least in standard things, rho has to always be positive for all sorts of standard things obeying the usual theorems, But p can be negative, and if it's very negative, the universe a double dot will be positive. Therefore, the universe will be accelerating. Now, notes on hydrogen pressure. This is not hydrodynamic pressure in this equation. Hydrodynamic pressure is nabla p, is gradient forces. These are not gradient forces. These are relativistic pressures. How do we know they are relativistic pressure? Because it comes p over c squared exactly, which is rho v squared over c squared. As long as v is smaller than c considerably, these pressures are negligible compared to the energy density. So that's why they only become important for things like photons or fast neutrinos or things like that. They're not important for galaxies, which move at relative to each other with hundreds of kilometers or thousands and so on per second. Okay? They're not important for normal matter or cold dark matter, which will come tomorrow or the day after, things like that. They're important for photons, for fast relativistic particles like neutrinos. They may be important for exotica. They are important for exotica like dark energy and inflatons and things like that. Okay? And therefore it acts like mass. If it's positive, it decelerates. And it's negative, it accelerates. Important point, because some people think like this is like, again, a movement with a gas, more pressure. No, this is a relativistic mass equivalent. Mass equivalent, not hydrodynamic pressure where you increase the pressure, things will accelerate. Okay? It's opposite. Is this clear? This pressure is equivalent to mass, not to hydrodynamic pressure. It comes from, that speed and relativity contributes to energy, which contributes to mass. Is that clear? When this is positive, it acts like mass. When it's negative, it acts like anti-mass. It's not pressure that makes hydrodynamical force. And move it with a gas, There is a force on the gas canister, not because there is pressure inside, it's because there is a pressure difference. Nabla P, discontinuity at the boom. There's no discontinuity zero, there's no Nabla P is zero. It's a homogeneous isotropic unit. This is not hydrodynamic pressure. Right, what is it then? So how do we get our Friedman equation here? This is usually called the one before the acceleration equation, and this one the Friedman equation. Okay? But this is a convention. Sometimes they call both the Friedman equation. So we can use the first law of thermodynamics, and because we are an isotropic homogeneous universe, there's no TdS. Entropy is conserved. DS is zero. There's no heat transfer, things like that. There's no viscosity. We took out the terms VI, VJ, average. Okay, we took out the terms VI, so there's no viscosity. We kept the term VI, VJ average, would be viscosity, and we need to put TdS. There aren't, because nothing is actually moving to have any friction with respect to it's just expanding nicely. Okay? So this is the first law of thermodynamics, and if you put the internal energy being the rest mass energy of the stuff, rho c squared, which is the only energy in the co-moving frames, right? Because things are not supposed to be really moving in the local frame. All right, so this is really the only energy. And then put this guy, you get something called the continuity equation, which is in general relativity, this is equivalent to divergence of the stress tensor being zero. You took that with Adel last week, right? Divergence of the stress tensor of the energy momentum tensor being zero. Well, in case you didn't, this is what it is. Take the energy momentum tensor for that contains any pressure and density, and do the nabla T nu is zero, and you get this. But we did it another way, which is equivalent, at least for our case, from the first law of thermodynamics. Okay. Once we did the first law of thermodynamics, we can put it into our acceleration equation, and you get a total differential, which is something similar to an energy integral, but including things where there is pressure. Galaxies don't have pressure. They're not relativistic. Matter, normal matter, usually doesn't, at least when they tune. What has pressure is things like photons, like we said, neutrinos, and other relativistic particles if they exist, and exotica like inflatons and dark energy and so on. These things can have pressure. So we have now our equation like before with the constant. We still don't know what it is. It was 2Es over 2R over R S squared in the I think I'm using different conventions. I think ES over RS squared. It doesn't really matter anyway. But that's what it was, ES over RS squared in our nice Newtonian derivation, or simple Newtonian derivation. Now this is a total differential. This is rho A squared d by the A rho A squared. So we can easily integrate our equation. Oh no, there is a 2 because sorry, because this is A dot squared over 2, so I multiply. Okay, and this now it's 8 pi G dot. Right. So that's it. This is our equation. But we still don't know what that thing is. Now we accounted for relativistic particles. We have pressure in our equation. For example, who knows that radiation pressure is third rho or third E of the radiation? Okay, one person. Okay, Stefan Boltzmann. Stefan Boltzmann law and Carnot cycles and so on. You can actually derive it very elementary. Anyway, pressure of radiation on third E or third rho in our language. Okay, this thing really went analysis. Okay, for that you need a metric. To start interpreting this thing, we need a bit more from relativity. Now we need a metric. Not only to know what our constant is, but also to know 2e over r squared, what is it exactly? And also to start comparing in observations. How do you compare this? We don't know what the scale factor is or things like that. How do we compare this Newtonian analog or semi-Newtonian, semi-relativistic thing here with observations? We have no idea. We need to start measuring things and so on. We need a metric to measure time and space properly. Meaning having a proper distance, for example, like in the bottom of this thing. So, first of all, because again we have a homogeneous universe, people or whatever, observers can synchronize clocks. How can they synchronize clocks? They can do it by measuring, for example, the density, which will be the same for all of them. If they know they are in a, even if they don't really communicate, if they know that this is homogeneous isotropic universe, they would know somebody very far away who has the same density, what would be his or her situation or time. So you have a cosmic time, you can do it. If you want a careful exposition of that, there is in Peebles' book, Physical Cosmology, a nice, careful discussion. But I think it's very intuitive. In fact, much better than local density. You will measure, when you talk about the cosmic microwave background, people can measure the temperature of the cosmic microwave background and know at what time they are. So there is a sort of cosmic time that they can use. Once they have the cosmic time they can use, they can write their metric like that. Or they can reverse the sign if they are physicists who like the reverse signature. But they can have this positive and the other negative, doesn't matter in the end results too much. Like driving the people equation. If they write it like that, then they can write a time component that is normal to a space component. Meaning the time component slices are independent and perpendicular. So there are observers on each time component trying to agree on the same time. Okay, and they can measure proper distances at that given epoch. The dt between them 0. Okay? They have the same clocks. And then there is an dl component that expands or contracts if you are in the contracting stage of a universe. Okay? So this will be ruled by the Friedman equation, which we already derived heuristically. And now, what is the element dl? It can be Euclidean, flat universe, no problem with that. And people think that we are living in such a flat, spatially flat universe. Or it can be curved, this dl. Now, how is it curved? It can't be any arbitrary curvature because we had imposed what we call maximal symmetry, isotropy, and what is called maximal isotropy and homogeneity. So the curvature has to be constant. It has to be one curvature in all directions. It has to be constant from one place to another because of homogeneity, and the first because of isotropy. So there's really only one curvature. And therefore, there's only two ways that it can be curved. It can be constant positive curvature or constant negative curvature, or 0, flat. That's the third way, which is not curved really. Okay, 2 ways to be curved and 1 way to be flat. Or 3 ways to be curved. How you call them. Okay, right? So, and that's what change with time. Okay, because the radius, not the radius of curvature will change. Because of the scale factor. But this characteristic thing will not change. It is multiplied by changing time, but it is fixed. The way you fix it depends on different conventions, but it's fixed. So here you go. Let's do a closed space, a hypersphere, a 3-dimensional sphere. It's a 3-dimensional analog of a 2-dimensional sphere. You can, I'll do the closed, and you can try your luck with open, saddle, hyperbolic. So let's take 4 coordinates in a 4-dimensional space, not space-time, 4-dimensional space. And let's do polar coordinates on these things. So if we take the chi out, if chi is 90 degrees here, these things will die. And you just have the normal spherical coordinate. So a spherical coordinate with theta, phi, and chi instead of theta and phi only. Okay? And the radius. So, and this is the definition of a sphere. An r sine chi is a radius on a 2-sphere. Subsphere. Okay? That depends on chi, parametrization. So this is a definition of a 4-sphere, of a 3-sphere embedded in 4 dimensions, like the definition of a 2-sphere embedded in 3, which you take this one out. And the definition of a circle, you take these 2 out. Okay? Is that clear? Right. So we use this sort of thing to get the line element, the DL, the spatial line element. That's what you get. It's very easy. You just do it. And when you do the hyperbolic, if you do it, you just replace these by shines, and then you have a minus over there. And that's a hyperbolic. Negative curvature. This is positive. Okay. Flat is obviously, this goes to infinity. Really. It's Euclidean. It's a 3-plane, okay? Which is the space we live in, like that. At least locally. Globally, people think we are. So here's how it looks like. This is, I don't know what happened here anyway. So this is how the metric looks like. You can do R, you can do this substitution. R is R, a small r is R sine chi, what we call the radius of a 2 subspheres. So there are 2 subspheres. I took here there's parametrization in terms of phi out, so it's a 2 subsphere. Phi is an additional component which can't draw, of course. So these are 2 subspheres, and in this projection they look like circles. This is the geodesic distance, r chi. This is the radius of curvature of my space. And if I take the substitution, coordinates on these circles, it's not really a polar coordinates anymore. Polar coordinates, you would have that and k equals 0, which is a flat space. This is not a flat space, you have kr. If k is positive, then you have positive curvature. If k is negative, you have negative curvature. This is the radius of curvature. Here, this is, so you're starting to know, by the way, what is our constants are in the Newtonian. Right? So this is the metric here. R is Euclid. This is important. R multiplies angles. So it's the Euclid equivalent Euclidean distances on 2 subspheres that multiply angles. Angles in 2 dimension, d theta, and or 1 dimension, d theta, and 2 dimension, d phi, d theta, which are important because these will define our distances. Okay. So it's a Euclidean distance here on the 2 subsphere that defines them. This thing, R small. This is R capital, geodesic distance. This is equivalent to the co-moving distance, and that we'll discuss tomorrow. Okay, and this is our angle chi and theta. Phi will be normal to them later on. Okay, right? Okay. We can put then the expansion in time, and this is called the FRW metric. Friedman-Robertson Walker metric. You'll play with it, right? Okay, and if you want to do some analytical stuff, there are lecture notes, as I said, by Terera and also by Daniel Norman, which are not too complicated, if you want to try it out. To do the GR, which we'll show in the next slide. But before we show the GR in the next slide, I have one slide. Cosmology with the background cosmology. But before we do that, we put our 2 formulations of the metric. Both are important, or at least interesting to be used in some situation. And also to mention that there are different conventions. Sometimes you'll see k minus 1, 0, and plus 1. And in that case, A will not be a dimensional scale factor like we did, but will have dimensional distance. A would be in meters or light years or kiloparsecs or megaparsecs or whatever it is. Okay? But we use this convention here. Okay, so this is important if you want to actually calculate it. We use the convention that K, we derived it this way, and it's 1 over R squared, plus or minus, depending on positive curvature, and it's a radius of curvature. It's nicer in many ways because then you can scale the scale factor to be 1 today, and very small in the early universe, and you get that, you can, otherwise scale factor will be in units of gigaparsecs today. Usually it's a Hubble sphere. They fix it to the Hubble sphere. And you don't know what a co-moving gigaparsec was at the beginning, at the CMB, for example. It becomes complicated for no reason, in my opinion. Okay, so these are the three cases. Shine for negative curvature, sine for positive curvature, and flat for zero curvature. These are the three possible Friedman universes. And this is how it looks like in GR. Okay? Since you did a lot of GR already, so maybe it doesn't look frightening when I do it on the first day. Since you did a lot of this stuff. So this is our metric, and these are the diagonal, these are the elements of my energy, no, these are not energy momentum, these are the metric tensor elements. They can all be made diagonal because of the isotropy and so on, and they're the same in all slices, and because also we know from isotropy again and homogeneity that the metric tensor is diagonal, so the energy momentum tensor, and they are related. So if this is diagonal, these guys are derivatives of the metric and derivatives of the metric. So this is the Einstein tensor, which is the Ricci tensor times the metric times the Ricci scalar, and all this contains the metric and its derivatives, the Ricci tensor, for example. But this is usually, as Adel and others, and maybe Alexei mentioned, this is really usually complicated stuff. But in our case, it's relatively simple, and you can do it at home, actually. Especially for the flat case, it's not that difficult. But takes a lot of, tamrin and exercise. So these are the components of the Ricci tensor. For example, this is the only surviving components will again, like energy momentum tensor, will again be the time components, which correspond to the energy, the rho, the Poisson equation, really, in some sense. Yeah, and the time component and the space components, which have to be the same and contain the curvature. Okay? The space components of the area. These are the I and J 1 to 3. These are space components. They contain the curvature, and they're all the same. Okay, like the pressure is all the same. Okay, and this is the time component. And this is the curvature in the time direction, so to speak. So when we, another point, when cosmologists talk about a flat universe, they don't mean a flat space-time, because a flat space-time wouldn't move. It wouldn't have any dynamical equations, okay? They mean a flat space. They mean dl is 0, okay? dl is flat, okay? They don't mean the dynamics is. The time component, they always remain. And that's where you get your Friedman equation. You can see it already, the A double dot of the A. You can see it already from here. These are the components of your acceleration equation. And if you look at the acceleration equation, of course, the details are technically a lot of work, but you can see it already. And so on. You can see it coming up. And so what you do, you take your metric and you put it into these, we have already our energy momentum tensor. It's in diagonal form rho PPP. And this is, you get your Ricci tensor by putting this metric inside the formula for the Ricci tensor, and then you contract it and multiply it by G nu and so on. By multiplying by G, there is, no, there isn't. Sorry. And so you get your equations. You'll get again your acceleration equation, and you'll get this thing here. You'll get the Friedman equation. Instead of the 2Es over Rs squared, you'll get that. So it turns out our big constant that we were looking for in the Newtonian approximation we could never find, we didn't know what it is connected to curvature. So it's connected to the curvature of your universe. It's a constant that is connected to the curvature of your universe. Okay? In fact, you'll see this is like 1 over r squared, as we saw. You'll see that this is connected to the time that light takes to travel the radius of curvature of your Friedman universe. Okay? Because this is 1 over r squared. And a squared is the same scale factor. For a given, if we wanted constant, we put a equal 1. This would be r squared over c squared. And this is connected to the time, of course, the squared of the time, the inverse of the squared of the time that light takes to travel the radius of curvature of your universe. Okay, so that is our Newtonian constant, which involved a radius and an energy. Turns out the energy is c squared, energy density, energy per unit mass. The energy is c squared, and radius is the radius of curvature. Okay, so things become clearer when you put the metric in the equations, right? Okay, so we put your metric tensor inside the Ricci tensor, and you put your stress tensor, your energy momentum tensor on the right. You get these things downstairs. Okay. You have a time component which is always curved, even for flat, so to speak, spatially flat, and a space-like component which could be flat or curved, depending on what. We would want to know depending on what. How do we know then? Okay, we did our nice exercises in Newton's laws on GR and so on, and we found that this constant is the curvature. This is not enough if we're doing science. What is the curvature? What is it in our universe? That's the science. All that is nice exercises. The only science we did up to now was the observations of the galaxy distribution and the assumption of isotropy and homogeneity. But Einstein assumed that already even before there was any science. So he thought, let's make it simple and assume isotropy and homogeneity. The second bit of science is to try to measure these things. We'll assume that K is 0, flat universe. Then we define something called a critical density. And the critical density is simply putting this equals 0 and calling it rho c. The Hubble parameter, as we defined it, is the A dot over A. This is not constant. It's constant when it's now, but it can vary with time. Okay? So rho c is that, by definition. We take our Friedman equation and we put this 0. Now, a couple of important points which relate to inflation and things like that. Let's say we have a matter-dominated universe. Then how does rho change in a given, when the universe expands with the scale factor? Can anybody guess? Well, we already did it. How does rho change with the scale factor for a given volume of a conserved mass? What is density? Mass over volume, and we keep the mass constant. So how does rho change when we change the volume? Which is inverse a cubed. Okay. But this is inverse a squared here. So therefore, if we go really back in time, this will always be small compared to that, because this is 1 over 0 cubed, so to speak, okay? Any mathematician here will, very small, 1 over epsilon cubed, and this is 1 over epsilon squared. Therefore, the ratio is like epsilon. Okay, so this would be, so any universe that is, for example, matter dominated is even worse with radiation, we'll speak later, is like flat. This is negligible. Behaves like a flat universe. Any universe that has matter or radiation early on, and why? Now look, the reverse is also true. If this k is big, as A increases, the curvature will dominate, and this thing will become negative. For example, if k is positive. And it can't be negative. That means that the universe will start to contract. Okay, and it will contract very fast, because this is 1 over a squared and the other guy is 1 over a cubed. So there's a sort of fine-tuning here. Why are we fine-tuned to be most of the time flat? There's probably a structural formation also. If you're not, if you are too positive, you'll never make galaxies, it will be too short. And if you're too negative, you'll never make galaxies, because it will expand fast. You need very large perturbations to make galaxies. We'll talk about that if we have time on Wednesday or Thursday. Okay. So there is a sort of fine-tuning there, that our universe seems to be nearly flat. Why? Well, one of the proposals is inflation. It stretches the universe early on so that it becomes nearly flat, as Alexei probably told. Okay? Now, so therefore, the curvature and so on is connected to the ratio of the real universe to our flat universe where we defined rho c, k equals 0. Okay? So this rho is equal to rho c, because we live in a flat universe, this is 0, and k is 0. Okay? And this is what people believe is true. Flat, spatially flat, not space-time. Otherwise it wouldn't move. Okay, and again, this cannot change sign, because all these guys cannot change sign. K is either positive or negative or 0, and this is positive, 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 so this cannot change sign. If this is positive, it remains for all time positive. If this is negative, it remains for all time negative. Okay? Depending on your K. So, it's fixed. It's destiny. Cannot change. Okay? Whatever you put. So what then is K? How can we measure it? We need to start measuring it. To do science, you need to start measuring it. We don't. That's why the Newtonian approximation wasn't good enough. It's not because it's not elegant mathematically, but because, well, maybe some people think so, but also because it asks conceptual problems, of course, that what is the universe expanding into? Okay, so the Newtonian derivation has these conceptual, let's say, epistemological problems, but it also has scientific problems, that we didn't know what our constant is, we could not put photons, we could not put things like the dark energy, we'll find this there, and so on. So it has other problems to Newtonian, scientific problems. Okay, so but we have gone beyond these scientific problems and we want to measure. So what is K? K, if you fix at the equation that we wrote in the previous slide, here, at t equals now, h becomes h naught, and omega becomes omega naught, and this is our K. So it doesn't matter when we measure K, because K is an invariant. If K is positive, it's always positive. If K is, that's why some people prefer -1 and 0 and +1. But it creates other problems. Okay, but some people prefer the -1, 0, and 1 because of that, to make clear that this is an invariant. Okay? So they have a point on that. So you can measure the Hubble constant, and it's measured since Hubble, not very precisely, but since Hubble people measured it. And next talk will show how he does it, he did it, and how people do it nowadays and so on. But let's, well, not in detail, but we can give a hint. But if you assume for now that we can do distances, and we can do velocities somehow, through a Doppler effect, let's say, heuristically, we're gonna do much better than Doppler effect the next talk. But let's say the galaxies are redshifting away, so I measure the change in, the change in light and the change of the other path lambs, and then so light it goes bluet, this sort of thing you have. So you have this. Let's say we are measuring simple Doppler, and then for small distances compared to the horizon, it is again more or less a Doppler effect. You can consider that if you want. So, and this is your distance, and you plot the thing, and you get a straight line. The slope, just as you do in your experiment in the lab, you measure the slope, and you get a value which is the Hubble constant. Okay, local Hubble constant, because these are not cosmological distances. These are the sort of distances that are within the Hubble sphere and where you can do your Newtonian approximation. A few hundred megaparsecs is very safe for Newtonian approximation. Up to a gigaparsec is extremely safe. More than that become some errors can turn. But not much more. The errors become very bad maybe at 5 gigaparsecs. And not disastrous, but they become significant corrections. Okay. And you can't, of course, do outside the horizon with the stuff that Alexei was talking about with Newton, but that's another stuff. Okay? And how do we measure the redshift? We see the same lines and connect them. We see the same spectrum and match it. And these are the different wavelengths. And so we get V from it. Tomorrow we'll explain how that is done in a better manner, okay? But let's say we can do it like that. Okay? Then you can measure this. What you need is rho, no. And people were trying up to the late 90s to measure this rho mode very, very carefully. By counting galaxies, by counting the dark matter, by making, adding up the mass to just measure the density. And it's hard work, and lots of people are working on it, very smart people. And by measuring velocity fields, assuming the large-scale velocity fields were due to structure formation, which we'll talk about later on. The velocity fields, they map the density field and so on. We can talk about it tomorrow, okay? Or on Wednesday if there's time, or in discussions. There are ways to try to measure directly. Anyway, what did they get? They get omega 0.3, which is less than 1. They got not a flat universe, not a closed universe, they got an open universe. And this really annoyed the inflation people, because they wanted omega equal 1. Because if you have inflation, you get a flat universe. You stretch it e to the 60 or e to the 100, or whatever times, depending on how many e-folds you have, And you should get a flat universe. You have spatially flat. You shouldn't get one with omega 0.3. And why 0.3? Why not less? Oh, no. Well, again, if it's much less, you wouldn't have galaxies. So they talked about the anthropic principle and things like that. We're in a universe where this is fine-tuned in this way. Okay? But it turned out that this is completely wrong because rho, or at least we now think this is completely wrong because it was discovered through completely different methods that most of this rho is not made of things you can measure like that. It's not made of things of matter or radiation or things you can measure with a meter. It's a completely different thing. It could be, we don't know what it is, but it could be a cosmological constant or an inflaton-like thing that is a scalar field, or a thing that are completely unknown and exotic, and this blew the whole cosmology into a new world. From 1998 and 2002 with the WMAP, which I'll speak about lecture on Wednesday. I'll speak more about Planck, but it's the same. For our purposes. And so, it turns out you can't do that. What can you do then? What you can do is try to solve the equation directly and try to compare it with the history of the universe. And he started being able to do that in the late 90s because the telescopes got better and they could measure larger distances, way back into time. And there's defined standard candles we'll talk about tomorrow. Okay? So you could solve this equation. So to solve this equation, you needed a relation between rho and A. Right? Because it's an equation into unknowns. So you need to close it. Now, if you put matter on radiation only, radiation is negligible for reasons we will see in the late universe. Matter goes as A cubed, radiation goes as A to the 4, the density. Do you have any idea why? Why radiation density would go 1 over A to the 4 and not 1 over A cubed? Like matter? Because we said that matter goes 1 over volume, 1 over A cubed. Why would radiation go 1 over A to the 4? When you expand it. Why does the energy density of radiation, the number of photons goes as 1 over A cubed, but what happens to a single photon? انت بتغش عشان عارف لا no بغلس right. Yes, like you were saying, it gets stretched, right? The photon gets stretched and its wavelength increases, its new wavelength increases, its density, its frequency decreases. So when the frequency decreases, h mu decreases, so every photon is less energetic. So the number of photons goes down as 1 over A cubed, like the number of atoms, for example. But every photon energy goes as 1 over A, because like nu. You know, Planck formula, not the Planck spectrum, Planck formula, E equals h nu. Right? So, and then you could have the exotica. Cosmological constant has constant energy density. You expand it, and it doesn't go down as 1 over A cubed, it doesn't go 1 over A to the 4, it's a constant. It has to have potential energy then if it's a field. You can't do that without it if you want. Yeah? So you can't have an energy density constant for normal gas or a field. Okay? So this is like a generalized equation of state. This is 0 for matter, galaxies and things that are not relativistic. This is, the pressure is 0. It is a third for radiation. It is constant for a cosmological constant. And then you can put it in our continuity equation, or first law of thermodynamics, depending on your preference. And you get this for W, 0, 1, third, whatever. You get that. Then you'll see that the universe, when we were very long ago and far away, or things were far away, was radiation dominated. Because radiation goes, like diverges as 1 over A to the 4. So as A goes to 0, it goes to infinity faster than this guy. And this guy is always constant. So in the very beginning, so to speak, after inflation, we have radiation domination. The universe is dominated by the radiation omega, by the radiation density, a third here, okay? And then later on, it's dominated by matter, and this guy, Naim, it's constant, but these guys are going down on a log-log plot. As you know from experimental things, power laws look straight lines on log-log plots. So these are log-log plots, and these are power laws. This goes down, and this goes down, and this goes down. So radiation domination, radiation matter equality, an important epoch in cosmology. and lambda domination, or whatever it is, dark energy. Here it's lambda, constant dark energy. And remember we said that it causes the universe to accelerate, and it has a negative equation of state. -1, sorry, it's not 1, so it's minus. -1, rho is constant. So what you put here is W minus 1. Okay. So you put W minus 1, you get, this is constant. -1, 1 here, so this is 0, and rho is constant. Right? Right, so here we go. So we can put these things in our Friedmann equation, and for a flat universe, suppose it's a flat universe, so we put k equals 0, just as an exercise, then you get, it's very easy. Put rho minus a cubed minus 4 and so on, and put it in here, and you'll find, we mentioned this already, this is the stuff about early universe being flat. Focus here, we put our 1 over a to the 4, we get this one. 1 over a cubed, we get this one. This is the inflation. It is like inflation. But the interpretation could be different. Could be similar or different, we don't have that. But it's like inflation. This is like what they call a de Sitter thing. Okay? So this is exponential. You put, because you know, you put rho equal constant here, what do you get? You get log and so on. Yeah, solve it. It's trivial. Yeah? Put rho equal constant here. What do you get? Right? Okay, so tomorrow we'll try to determine all that to observables so that we can know the curvature of the universe, the expansion rate, its age, and contents and so on. Try to use observations to fix this thing. We already have a good idea what we want to do. We want, instead of taking the limits here of radiation only and matter only and lambda only, we'll put everything, and we'll put the curvature too. Okay? And see what values of radiation, matter, cosmological constant, curvature matches what we really observe. But then we'll have to define what we observe and how to observe it and relate it to the theory. Once we have done that, we can fix our cosmological parameters. And then say how much dark matter, how much dark energy, how much radiation we know from the CMB directly, but yeah. And it's not important in the late universe because it goes down as 1 over 8. Okay, so this is our thing tomorrow. I'm already over time, so any questions? Comments? Complaints? No complaints? واجعين أوي. من زي That's it. All right. Let's do